So first, I still want to thank the organizer for having me to be here. And today I will discuss the future opportunity from CMX experiment. But before talking about the future, I'm not sure if you have an idea about how many heavy flavor measurements we have already achieved over the past few years. So I was curious about that. So I made a website to collect all these results. So as you can see, yes, it has been a great success from the whole heavy flavor community that we measure different particles with different flavors and different multiple observables. And also we perform some quite differential measurements. So standing at this point, we must curious about what we can achieve in the next stage and what we can where we can get in the end. So this is a blueprint of the LHC run in the next few years. Now we are here at the end of the long shutdown 2. In 2015 and 2018, we collected a fairly large data set, but in the run 3, starting from next year, we will have 3 times more statistics than that. And in run 4, we have another data set with a similar size with run 3. So the increase the increase of the luminosity is definitely exciting because we can achieve higher precision and new opportunities for new probes. But what we also need to think about is how to use these large data sets in a more efficient way. So between the run 3 and run 4, CMS will implement its phase 2 upgrades. So these upgrades will include the improvements of almost all the sub-detectors from CMS. So first of all, there is a significant upgrade of the inner tracker. With a higher granularity, the tracker will provide a better resolution. So this is particularly helpful for heavy flavor because we heavily depends on the quality of tracking and the vertex reconstruction. Another big change is the coverage of the inner tracker will be enlarged. The pseudo-rapidity range will be extended from 2.4 to 4. These will allow us to study the longitudinal dynamics and help us to construct and understand and construct the 3-dimension heavy quark dynamics in the Quark-Gluon plasma. So the next improvement is the trigger rate and the data acquisition rate. So this dramatic improvement will allow us to implement more complicated triggers and collect a large number of mean-biased events. So for the heavy flavor studies, we are often interested in very low PT area. So in this area, it's very difficult to find a signature to trigger the events online. So the mean bias data set is particularly important for us. The last but the most important upgrade is a new MIP timing detector, or MTD. So this timing detector was actually proposed to solve the high pileup issue in proton-proton collisions in the high luminosity LHC area, but its high precision determination of the arrival time of the signal can serve a perfect time of flight hadron particle identification. And this is so important for heavy ion to suppress the high level of background of combinatorial backgrounds. And this CMS hadron PID has a fairly large coverage of acceptance. So there are two parts of MTD at both barrel and end cap to achieve this large acceptance. So as we know, for the PID using time of flight, the performance is better if we have a longer distance of flight. But if we compare with other experiments, the CMS actually has the smallest, the shortest distance of flight. But the excellent timing resolution save it. So the design timing resolution is about 30 picoseconds. And this helps, this makes MTD comparable with the PID facility in other experiments. So the Hadron PID mainly distinguish kaon, pion, and proton in our case. So this slide shows the separation power mapping the whole kinematic phase space. So we can see in terms of transverse momentum, MTD can decently separate kaon and pion from 0.7 GeV to 2.7 GeV. And for the kaon and proton, it can separate from 0.7 GeV to 4.5 GeV. So in terms of the rapidity, we in the x-axis, we know that at least Hadron PID focuses in the mid rapidity, and LHCb only covers the forward region. So CMS MTD provides a complementary and unique information for the Hadron PID. So the previous slides shows the performance of individual charged particles, or say daughter particles. And in these slides, I want to translate that into the impact on the heavy flavor hadron reconstruction. So for D0, we reconstructed by the K-pi channel. And on the left-hand side, we show the invariant mass distribution without MTD using the statistics equivalent with 1 year of REV4. And on the right-hand side, we show the similar plots, but with MTD implemented. So we can see there is a significant improvement on the signal to background ratio if we have the PID information from MTD. So because the Hadron PID actually mostly distinguish the proton and kaon from tons of pions, so it will have a stronger impact if the channel has a proton there, or if it have more daughter tracks. So the lambda C is an excellent example for this. So here, what we show is the background rejection with MTD. So the numerator is the background with MTD, and the denominator is that without MTD. So on this plot, the more blue it is, the better performance is. So we can see for lambda C, it has a more significant improvement compared to D0. And this may also enable some new probes that we cannot achieve before with many daughter tracks, like the B+ to D pi. And this will help us to extend our beauty measurements to a more.
Wait a second, we had a small technical problem here, but it's fixed. So I guess you can resume, yeah.
Okay, did I miss anything?
We probably only missed 20 seconds of what you said. So I guess we are almost on track.
Okay, I will just quickly repeat that.
Yeah,
so
thanks.
So similar to lambda, so lambda C have two daughters, and similar to that, we have some other new props like B meson to D pi. It also has 3 daughters, and this we cannot achieve this before because of the high combinatorial backgrounds. But with the help of MTD, we may achieve that, and it will extend our beauty measurements down to a lower PT. So previous slide, the previous slides is more about the performance, the technical performance of MTD. And from this slide on, I will discuss some expected performance of physics results. So here is the current open heavy flavor nuclear modification family from CMS using existing data. So for we measure different flavors. For charm, we have the prom D0, and for beauty, we have the fully reconstructed B meson and its daughter D0 and D meson and gypside. So with these measurements, we have a preliminary picture of the flavor dependence of parton energy loss in the Quark-Gluon plasma. And we indeed gain a lot of insights there, but it's still not good enough. So here, here is the projection of RAA for the high luminosity LHC statistics. So we can see we will have a high precision RA measurements over a very wide kinematic range for all the flavors. So at the low PT side, we have the capability down to below 1 GeV, and at the high PT, CMS has a unique access to above 100 GeV. So these wide kinematics will help us to study different processes that dominate in different kinematic range. So for example, we can have a full picture of the relative relevance of collisional energy loss and radiative energy loss that dominates in different kinematic range. And not only we can improve the precision of our current measurements, we can also enable some more differential measurements that we can have a even detailed picture of what we want to know. But there are two things I want to point out here. One is that in this plot, the luminosity at low PT are way too conservative. That actually with 2018 data we have collected is already achieved these luminosity. Another thing is the MTD improvement is not reflected. So in the end, our performance of these measurements at low PT will be much better than what I show here. So next, after the RAA, next we move on to the flow. So here, what we show is the expected performance of D0 V2 with and without NTD. So if we focus on the results with MTD, that is the solid triangle markers, we can see we will have a very, very nice precision over even down to a very low PT, and we can have a new access to 0 PT with MTD. And even at the lowest PT bin, we have a fairly good precision there. So the MTD doesn't only improve the precision of D0 RV2, it also enables us to enable the measurements of lambda CV2. So here, with the colorful markers, we show the expected performance. If we focus on the result with MTD help, with the help from MTD, that is the red markers, we can see we can also have a reasonable precision for lambda C, and the lowest PT it can access is down to 1 GeV. So the V2 measurements of lambda C doesn't only provide more information about charm collective motion, it can also provide a new test of the number of quark scaling. So we know that in the light flavor sector, magically there is a very simple number of quark scaling for all the particles. And with D0 and lambda C, we can extend these tests in the charm sector. So let's make a quick summary of RAA and V2. So here is, I collected almost all the theoretical calculations of RAA and V2 from in the market now. So we can, as we have already, if we compare this with what I have already shown, the experimental precision we can achieve in the next stage will impose a very strong discrimination power to the theoretical calculations. And on the other hand, our experimental uncertainty will become much smaller than the theoretical uncertainties. So if you ask me, are the RAA and V2 good observables? I will say yes and no, because what we want further is that we want to decouple different process, and they are mostly actually coupled, be encoded in these RA and V2. So I want to introduce the next topic, that is the correlation. So in the paper, in this paper, the author varied the internal diffusion coefficient and the energy loss mechanisms in their model, and they found for all the configurations, they can actually predict a fairly reasonable results for RAA shown on the left-hand side. But if we look at another observable, that is the azimuthal correlation between C and C bar quark, we can see these different configurations are separated. So these inspired us that the correlation might be a more sensitive observable to the macroscope mechanism behind the diffusion of heavy quarks in the Quark-Gluon plasma. So in the 2015, we measured the radial distribution between the D0 with respect to the jet axis. And at that point, we can only have the first result, but didn't have a good precision to address the final words. So on the left-hand side here, what I show is the projection of these measurements, but with the high luminosity LHC statistics. So as previous, the MTD gain is not reflected in these plots. So in reality, we will have a better performance. So not only the DJET correlation precision will be improved, but MTD can give us an opportunity to enable more new measurements. So for example, the jet itself is modified by the medium, as we know. So it's probably not a very good reference when we study the D0, the charm diffusion. So another measurements we can do is the correlation between photon and D0. The photon, we know it doesn't take part in the strong interactions, so it will become a perfect reference. Another measurement we want to do is the D0 and D0 bar correlation. So in this observable, we don't need to deal with the complicated situation for the jet modification. And on the other hand, the charm diffusion effects will be double because we see two D0s. So we believe these new measurements will provide us unique insights of the charm diffusion in the Quark-Gluon plasma. So the next topic is hadronization. So in another ECT star heavy flavor workshop in April, we saw a lot of very beautiful compilation from the current theoretical models. So here, what I show is the ratio of hadron RAA, actually the D0 RAA after hadronization, divided by the quark, the charm RAA, before the hadronization. So we can see different theoretical models give a quite different results. Although we cannot say this is purely from the hadronization process, because it also depends on your the spectra itself, but we can still have an impression that there is still a big disagreement on the hadronization mechanisms between the models. So I think it's important from experimental side to provide more constraints and information. So the most classic observable to study hadronization is the Bion to meson ratio. So here we show the lambda C to D0 ratio with and without MTD information. So if we focus on the MTD with MTD results, that is the red markers, we can see we have a very nice precision for lambda C signal in a quite wide kinematic range. And it also enables us to have a new access to the zero PT at zero PT. So these may help us allows us to measure the total charm cross section. And the three panels are actually three different rapidity ranges. So we can see the theoretical curves that most of the theoretical models predict a invariant result for in the longitudinal direction. That is, they don't really show any rapidity dependence. So the wide coverage of our MTD will provide information on the longitudinal direction that we can impose the constraints on in another dimension for the heavy quark hadronization mechanisms. Yeah, so apart from the light-light collisions, the hadronization in smoke system is also not completely clear for us. So here, what is shown is the lambda C to D0 ratio in P-light collision. The y-axis is the center of mass rapidity. So the forward region is covered by LCB, and the mid rapidity range is studied by Alice. So we can see somehow it shows it has a hint that the Alice result is higher than that of the from the LCB, but we don't know what happens between these two rapidity range. So the CMS MTD will perfectly fill this gap and tells us what will happen here and how to connect these two results. So apart from the bions, we can also use the strangeness heavy flavor hadrons to study the hadronization. So first off, on one hand, the strange quarks content will be enhanced in Quark-Gluon plasma because of the high temperature, and the heavy flavor hadrons may be produced by the coalescence between the heavy quarks and the strange quarks. So the enhancement of the strangeness heavy flavor hadrons will reflect the information of the coalescence. So here on the left-hand side shows the B sub S to B plus ratio using the current data. And the right-hand side shows the B sub S RAA projection using the high luminosity LHC statistics. So although we don't know how much improvement we can gain from these measurements, but we can still see that it is still a big improvement on the precision. And in the detector upgrades, we will also extend the muon detector acceptance. So that will help us to extend to the lower PT access because of the larger acceptance. So now let's move to some discussion on the quarkonium. So with the current data, we measure the upsilon, the ground states and excited states using the 2015 data, and we see this very beautiful sequential separation. But there are still some pities. First, at the most peripheral sites, the precision is not good enough to address a final words about what happened here. And for the upsilon 3s, we still don't have the capability to achieve the observations. And in the most central regions, we see some hint that there is a disagreement between the data and the theoretical models. And on the right-hand side, with the high luminosity LHC statistics, we can solve all of these issues. So over the whole centrality classes, we have a very good precision for upsilon 1s and 2s, and we can also have a capability to observe the upsilon 3s. So the lines here are from hydro model using different viscosity. So because the upsilon production is sensitive to the medium viscosity and the initial temperature of the medium. So we believe our results with the high luminosity LHC data will provide a very important input to these most fundamental characteristics of the Quark-Gluon plasma. So not only we can measure the production as a function of the centrality, we can also have a detailed differential measurements as a function of both PT and the rapidity. So these will give us a detailed information in all the dimensions, using the high luminosity LHC statistics, we have good precision to separate some small effects. So for example, the theoretical models predicts a small bump here because of the regenerations. So our precisions will have the capability to see if it's supported or disfavor it.
Jing, I see you still have 6-7 slides and we're entering the time for questions. So if you can speed up a bit, that would be nice.
Yeah, I will. So the next one is the upsilon V2. So using the current data, we scan different flavors, but among all of them, the one with the poorest statistics is the upsilon V2. So using the high luminosity HRC, we can achieve a fairly better good precision of it. So now we move to the small systems. So recently we observed the flow, the collectivity in the small systems in both the PLAD and PP collisions, but most of them don't really have a good precision to draw the conclusion that how the source of this collectivity is from. So using MTD, we can have a very nice precision for both prom D0, non-prom D0, and the GIPSI. So we believe this will bring us to an answer about the source of these collectivity, the collective motion in the small systems. And also we can, with more data, we can perform a more differential measurements by scanning the multiplicity classes to see when the collectivity starts taking place. In the small systems, we also study the cold nuclear matter effects that we can, the production of the heavy flavor mesons will provide the NPDF, the Gluon NPDF information that is an important input for our for the heavy ion studies. And also the lines here are the theoretical predictions with and without hot medium effects there. So we can see the production of the heavy flavor in the PLAD collisions can also provide us an information about whether there is a small droplet of the hot medium, the deconfined medium. So another way we can detect the NPDF is the ultra-peripheral land-like collisions. So in UPC, the photon-led collisions take place, and the coherent the photo production cross-section will reflect the gluon density of the nuclei. So by measuring the upsilon in UPC, we can gain the information in a wide X range. And if we vary the mass of the quarkonions, we can also scan the Q dependence of the nuclear modification. So we will expect this will also be an important constraint and input to the gluon nuclear PDF. The last one I want to mention is to detect the strong magnetic field in the heavy ion collisions. So this field is expected to be produced in a very early stage. And in this case, the heavy quarks are naturally have the advantage to detect it because they are produced very early because of their large mass. So they will extend a much stronger magnitude than the soft charges produced later, and it will also have the memory of the whole evolution of the field. So here we shows the performance, the projection of the V1, the directed flow of the D0 we can expect with MTD in high luminosity LHC. So the V1 is expected to increase as a function of the rapidity, but current measurements from Alice and Star are all focusing on in the mid rapidity. So the wide range of MTD from CMS will have an advantage to reach the region where the effect is the magnitude of the signal is higher. Yeah, so that this slide brings us to the summary. So in the high luminosity LHC area, the CMS will be the most comprehensive Quark-Gluon plasma detector with its new Hadron PID information. So I have already shown a lot of results suggesting that the CMS can perform a very high precision measurements in both the large and small systems, detecting both the hot and cold nuclear matter effects and in a very wide kinematic range. With the new MTD detectors, we can access the D0 and lambda C down to 0 PT, and it also enables new observables. And also an extension of the rapidity range of our inner trackers will provide new access to the study of the longitudinal dynamics and help us to build the picture of a 3D dimension heavy quark dynamics. So that's pretty much of it. Thank you.
Okay, thank you very much. Thank you for the web page, actually. And in principle, the time for question is over, but let's see if we have some questions. Yeah, no, please. We have to discuss, I think.
Yeah, but it's not a very important question. The last table that you showed, you said, yeah, for Alice, you have lepton PID that is not marked, but this is not correct.
It's in the LC3, right? The lepton, the muon PID.
It's not Alice 3.
It's not, sorry, it's not Alice 3. What do you mean? No, but in Alice we can identify muons and also electrons.
Okay. Okay, thanks.
Yeah, but it's a minor point.
I think we will allow the next speaker to correct your table, Jing.
I fix it.
Okay. It's fixed already, right? Yeah. It's online updating slides. It's perfect.
It's also a very minor point, but I would like to remind that, in fact, we at Nantes with Marlène Nargan were the first to investigate those effects of energy loss on the correlation. This paper appeared in 2014. So it would be good when you cite this early work also to include us. Thank you.
Okay, yeah, I will keep that in mind for this. Yeah.
Okay, thank you. Other questions remotely? No, here. Okay, so if not, let's thank Jing again.